Okay, we're back to the second half of the lecture number 4. First, let me answer the break exercise, talk about energy momentum conservation. Basically, we're saying that given you have the momentum conservation, the relativistic momentum conservation in one frame, then the condition that this same condition holds in a moving frame or another frame, in a prime frame, uh, not only you need the original momentum conservation condition, but also it must including the relative energy conservation. So basically, we use this gamma function relation. Remember, we use the u prime gamma prime u and the gamma gamma, and this, so anyway, we have these relations. So you, in order to check the validity of this relation, you just plug in the uh, for the prime system, just left hand side. So so uh, for this uh, uh, gamma UA gamma prime UA, we will substitute uh, by these terms. First, let's do the blue term, the U term. So we have the U term A, B, C, D. And then because there's a minus V term, same for every term, so I can factor out the minus V term. So I have this. Okay. So clearly, this line is just the condition for momentum conservation in the primes in the original coordinates, and this one trivially multiplied by c squared term just have momentum conservation. So therefore, in order to have momentum conservation, three momentum conservation, you must have energy conservation. Okay, both for the case of relativistic energy and momentum. So now we continue our discussion of the relativist for momentum. Okay. Now, momentum energy being component of the same vector, just like x time and this position, so it means they can be transformed into each other under coordinate transformation, just like x, y, z can be transformed into each other by rotations. Okay, so the exercise we just demonstrated that they must be taken together in any relativist treatment. You cannot just talk about momentum, you just cannot just talk energy, they must be taken together. So therefore, the most succinct way to write such conservation relations is to write as a tensor relations. And it's a 4 vector of A, 4 vector B equal to 4 vector C and D. So you notice the free index mu, so therefore this is a set of four conditions they should be taken together. Okay, and also if one writes this way, it's clear that this energy conservation holds for every frame because there's a tensor relation. So therefore, it's we can apply Lorentz transformation to every one of them. So it still holds in every inertial frame. So this is the way we should write the relative energy momentum conservation in terms of 4 vectors. Now, the energy momentum components of the 4 vector P has simple relations. So remember, the 4 momentum is scalar mass times the 4 velocity, and the 0 component is relative energy divided by c, and 1, 2, 3 component is the relative energy momentum. So you take the square of this, and remember the square involves covariant components, so there's minus sign, so it's minus e squared over c squared plus p squared. Okay, and we already, if you look in square of this term for m squared, the 4 velocity, we already shown that the 4 velocity squared is minus c squared, so therefore this p squared is minus m squared c squared. So you compare this two sides. At the right hand side, you get the relation between energy and the momentum, because this is so e squared equal to p squared c squared plus m squared c to the fourth. So this mc squared squared. this is a clearly a very important result. Then also, this shows that for massless case, when m equal to 0, E simply equal to Pc. So that's a simple relation between massless particles, energy, and the momentum. Okay, even though uh, it's a 4 vector, this has 0 length because if you remember, this is the length for p squared if m equals square. So and this means that you write out again same way you can show this came from. Now remember, there's a ratio of the relatives of momentum and energy. Pc over E is simply V over C. Okay, so therefore, in this case, for massless particles, if E equal to Pc, then of course the V equal to C. So therefore, massless particle always travel at the speed of light, because we didn't. All we needed to say is massless, is energy momentum relation, and then bump comes out. The V is always equal to C. So massless particle have no rest frame, can never, have no. It's always travels to C. Now, we can, as the application of full momentum for mass and for without mass particles, let's talk about Compton effect. First of all, it's a good exercise for relativity, but also it's a very important physics result. We'll see how it comes out. The Compton effect is simply you shine in this X-ray, but anyways, it's an electromagnetic wave acting on an electron, and you look at the uh, final light comes out as frequency and the momentum, and here is the recoil of the electron with energy E and free momentum P prime. Now, Compton made this discovery when he was an assistant professor at Washington University in St. Louis in 1923. It's extremely important because, of course, the idea that light can be, in some few ways, you can view it as particles was proposed by Einstein in 1904 in the context photoelectric effect. But people simply did not, in general, member of physics community simply did not understand, did not accept this. Even Millikan, who became famous for verify the photoelectric effect of Einstein, even he feel what the equation predict exactly what observed the experiment, but some ways he said I don't believe the fact light particles, because even you have seen it, but you don't, your gut feeling, you don't see how light can behave like it, because they were all conditioned light as wave, because the interference phenomena, all these just shows clearly it's the wave, and how can this be? And but Compton came along with this experiment, and this interpretation clearly shows the light can be treated as a particle that carries energy as well as momentum. Okay, and so then everyone just no question accepted this light can be a particle, and later on be called photons. Now, for this case, light scattering off electron, if light strictly is a wave, you expect the final frequency is the same, because a wave comes in, the electron popping up and down, and then radiates, so the same frequency. So the omega prime must equal to omega. But as you will see, if you treat light as particles, if you use like a scattering a particle of photon comes in, bouncing off, and you can see there'll be a shift, a frequency shift, about precisely this amount. So this is called a Compton formula of the frequency shift. We're going to use our knowledge of form momentum to derive this. So we're going to use this setup to uh, treat light as particles to derive this result. And we said conservation condition best expressed in terms of 4 momentums. So the initial photon momentum plus initial electron momentum is equal to final photon momentum and final recoil electron 4 momentum. Okay, it's saying there's 4 relations here because the index mu goes from 0, 1, 2, 3. Now, of course, electron p and p prime squared, 4 momentum squared is equal to minus m squared c squared. For masses of photons, the k and k prime square are equal to 0. There are no 4 vectors. And we're interested in finding omega prime. Omega prime is closely related to the 4 momentum k prime dot into 4 momentum of the electron. Okay, because we're going to treat the lab system. The p is at rest, has no 0 momentum. So now, if I replace p by this conservation, so p is equal to k prime plus p prime minus uh, k. So replace p by this. Okay, and again, k prime squared is equal to 0. So therefore, this is just k prime p prime minus k prime k. Then again, we'd like to replace the k prime because even though we say p is simple, but the recall momentum is complicated, so we want to get rid of it. Again, we're using this energy momentum conservation. So we square this equation both sides, so k plus p squared equal to k prime plus p prime squared. And again, using the fact k squared equal to k prime squared, p squared equal to p prime squared. So therefore, this relationship tells you the cross term are equal. So kp equal to k prime p prime. So this way, I can replace the k prime p prime by kp. So so k prime p equal to kp minus k prime k. Okay, so I just write this red relation here, and then you will see the next slides. When we work out the components, this 4 um, amount of 4 momentum dot products just recovers this Compton formula. So we're going to need to work out the components, this relation we wrote last time. And of course, this is just if I'm moving this k to the other side, so the factor of the k prime is k plus p plus k equal to k dot p. Now, when we say writing components, k, the momentum for vector, has energy h bar omega over c, and there's the momentum, and the magnitude momentum is, remember, is the mass of the particle, which just uh, just this is the energy over c. So energy is, of course, h bar omega. Energy divided by c is the momentum. Same for the k prime, and for the initial electron momentum, it's at rest, it's target at rest, so it has no 3 momentums. It's only energy, which is just mc. Okay, or energy over c is mc, so for energy is mc squared. So now we're going to work out this relation by plugging these various components. Now remember, this is now k prime with a low indices, so it's a covariant component. So therefore, the energy term have a minus sign because you're using metric to lower it. The metric has a minus 1, 1, 1. This minus 1 is, and same way, the k plus p has the written as a column vector written down here. And here for the k, I have also a minus sign in terms of frequency in this. And you just multiply them out. Okay, so for example, the first minus h bar omega prime with c multiplied this is c cancel, so this first term, and also this one to this here, just h bar squared, but have omega and omega prime over c squared. So you have the k dot k prime, the photon form momentum dot product, is equal to energy and times the cosine of the angle between them. Okay, so you plug this in, you divide by h bar m on each term, you have this relations. And you notice that each term has an omega prime, so I factor omega prime, so it's 1 this. And that's besides this relation we're talking about. Because on the left-hand side, here's omega. Okay. Actually, you probably see this looks less familiar to you because usually we write this instead of writing frequency shift, we write wavelength shift. Okay, so if you write in terms of wavelength, which is 2 pi c over omega, and then this relation in the yellow box becomes the wavelength shift, which is the h, not the h bar, h over mc, 1 minus cosine theta. Here's clear Compton posing the picture with the Compton formula written on the blackboard. Okay. By the way, this h over mc is called the Compton wavelength. So the Compton wave shift equal to Compton wavelength times the 1 minus cosine theta factor. So remember, it follows from the fact treating light as a particle carry energy and momentum, and from energy momentum conservation, you arrive this relation. Okay, that's the end of the 4th lecture. Here are the highlights. Remember, we say the proto-contravariant vector is a position vector with x with upper index mu, and the prototype covariant components is the del operator. It was del with lower index mu, and the Minkowski metric is eta mu nu is a diagonal with minus 1, 1, 1, 1 on the diagonal. So therefore, you can, for example, you can relate contravariant to covariant components, the zeros components, with a minus sign. Okay, because we can use the metric to raise and lower the components. And the 4th velocity is obtained by differentiating not back to the coordinate time, but with the proper time, tau. Okay, and the energy momentums are components of 4 momentum. And so with energy in the zero component, and there's relative momentum, and just from the fact that this p squared had to be invariant, we get this relation E equal to E squared equal to p squared c squared plus mc squared squared. And for particle with mass, its relative momentum is p gamma mv, and the energy is gamma mc squared. And for massless particles, of course, this m equal to 0, so equal to pc. And even though the has non-trivial components, but the 4 momentum itself have 0 length for massless particles, and the massless particle always travel at the speed of c. So the energy momentum conservation should be compact, written in terms of 4 vectors. Then it's manifestly covariant, and in fact, making calculation much easier. Keep track. So next lecture, lecture number 5, we continue to talk about the physics in terms of Minkowski tensors. In particular, we're going to talk about the electromagnetic field, which is turned out to be as a tensor rank 2. And once you realize that, the transformation we derive for electric field and magnetic field then can be understood. They are not vector, 4 vector, they are actually 4 tensors, rank 2. And then also the max equation can be written in what we call manifestly covariant form, in which written in a way is made so obvious that these equations are unchanged when you make a Lorentz transformation. Then we'll talk about conservation in a field system as expressed in terms of continuity equations. And then we introduce the energy momentum stretch tensor, which are the currents of energy momentum in the field system. Okay, and this is somewhat complicated subject, but it's needed because eventually the GR, the general relative field equations, are written in terms of this this tensor of rank 2. Okay, that's the end of the lecture number 4.